we now turn our attention to the issue of oscillations. And first things first, let's think about a mass attached to a spring, right? And we know that if we displace the mass this way, some length, and then we release the system, we know that it's going to oscillate back and forth, right? But it will always oscillate about this equilibrium position. Okay? So one of the first things to note is that oscillations occur about an equilibrium position. Okay? Now there's a couple of different ways of looking at this, but from a force perspective, we have Hooke's law, which says that the force acting on the mass is equal to the negative of the spring constant times the displacement. Okay, so this is what we call sometimes we call this the spring force. Okay, but it's really any elastic force can be reduced to a form of Hooke's law. Now the other way of looking at this is with the potential energy. Okay, so if you have a force that follows Hooke's law, or you have your potential energy where you have 1/2 times a constant times the displacement of your object squared, either of these are the condition for oscillations. Okay, and these are really the exact same condition because F is equal to the negative derivative of your potential energy, right? So if I take the derivative of 1/2 kx squared with respect to x, then the negative sign stays, the 2 from the square comes down and cancels with the 1/2, and I get kx. Okay, so if I have a potential energy function of 1/2 times a constant times a displacement squared, this implies that your system follows Hooke's law. Now, what's going on here? Okay, so if I plot as a function of position my potential energy, okay, this is a parabola. So my function would do something like this. Okay, so this is my potential energy function. And you'll notice, okay, that there's a spot right down here where the minimum is. This is your equilibrium position. Now, if your equation is explicitly in this form, then x equals 0 is your equilibrium position. But if your potential energy function is in this form, okay, so this is a parabola shifted to the right a units, right? So this would be like, if this is a, then your parabola would be shifted over here. Okay, and so notice that in both cases, the minimum is the minimum of your function, or let me state it this way: the equilibrium position if I can spell, the equilibrium position is your local minimum. Okay? So the equilibrium position is your local minimum of your potential energy function. Now, I really need to be explicitly clear here. When you have this kind of situation where your potential energy is 1/2 times some constant times your displacement squared, this is what we call stable equilibrium. Okay? So what that means is if I displace this mass a little bit and maybe push it up to here on the potential energy, it's just going to roll right back down. Now it'll actually do this. It'll oscillate. So this is exactly the spring mass system, right? It has too much kinetic energy to stop right at the equilibrium position. It'll roll right past. So you can think of like putting a marble in a bowl, right? And if you put the marble at the edge of the bowl, like toward the top, and let it roll down, it doesn't stop at the bottom. It rolls up the other side. Now, with real systems like that, of course, friction takes over, and eventually the marble will come to rest. But the marble will come to rest at the equilibrium position, at the stable equilibrium position. So, your stable equilibrium is the local minimum of your potential energy function. If you have a local maximum, so for example, if my potential energy function were an upside down parabola, okay, then the potential energy function would look like this. And as you can see, if I put a mass up here, and then I give it a slight shove, it'll roll down either side, and it won't come back. Okay? So stable equilibrium means that your object returns to its original position, and unstable equilibrium means that it runs away from that position, both under slight disturbances. Okay? So what that means for us is that when you have an equation in the form of Hooke's law where your force is equal to the negative of your constant times your displacement, this is what we call a restoring force. Okay? This is a restoring force. So restoring forces set things into oscillation, and non-restoring forces tend to accelerate things indefinitely. Okay, so that's kind of like the background here. Now, let's look at Hooke's law. So here, this is an example of what we call a differential equation. And it doesn't necessarily look like it right now. It looks like it's a linear equation. But remember that F equals ma. And so I can say that ma is equal to negative kx. But remember that a is equal to dv dt, which is also d squared x dt squared. So I can rewrite my equation as m times d squared x dt squared equals negative kx. And the way this is typically written is we move the m to the other side. Okay? And the only way you can take a derivative is if the thing you're taking a derivative of is a function. Now, 0 is, of course, an option. I can take the derivative of 0 and get 0, but that is technically still a function. It's a null function, but it's a function. So x is not a variable here. X is a function. And it's a function of time. So sometimes to remind ourselves, we would write it like this. Okay, so here we have x as a function of time, and the whole idea of a differential equation is that I have some sort of differential, whether it's a first order differential, second order, however many orders you have. Here in this case, this is a second order differential equation because we're taking the second derivative. Okay. And so the whole idea is we need to figure out what kind of function, when I take the second derivative of it, does it give me the original function back with a minus sign and with constants out front. Okay? Well, okay, so let me put it this way. When you take the second derivative, let's start with the original function back, because that's the most important piece. Okay, so what function? Now, sometimes there's multiple types of functions that might be able to be used. But generally, there's usually only one or two classes of functions. Okay, now, immediately you should think of two classes of functions. One is the exponential. Something like x of t is equal to some constant times e to the t, right? So if I differentiate this, what do I get? Well, I got my original function back, If there's a constant up here, then it would come down, so that's fine. But no negative sign. And the same would be true if I took the second derivative, right? So we don't have to bother going through that. So then you might think, wait a minute, what about a times e to the negative bx? I don't know what just happened. And a e to the negative bt, sorry. And you might be thinking, okay, but wait a minute. If I take the first derivative of this, I get negative ab e to the negative bt. Ooh, I brought down a constant out front and I got a negative sign. But when I take the second derivative, that negative sign disappears. So the exponential function is out. The second option is trig functions, particularly sine and cosine. So let's try sine. So if x of t is a sine function, then sine functions are typically written like this. Where omega is your angular frequency. Okay. And if I differentiate this, I get a omega cosine omega t. And if I differentiate it again, I get negative a omega squared sine omega t. Ooh, now this is interesting. So I get my negative sign, I get a constant out front, omega squared, and I get my original function back. Okay? So this is one of the functions that would work. Now, A here is your amplitude. So for the spring system, this would represent how far you displace the spring, or the mass rather, from equilibrium. Okay, and omega is your angular frequency. So if I compare this to this equation, well, let's put them over here so we can put them like one right under the other. So your spring equation says negative km x of t, right? And your sinusoidal second derivative says the second derivative of x with respect to time is going to equal negative omega a sine omega t, negative omega squared. So here is your x of t your negative signs obviously correlate, and therefore omega squared is equal to k over m. Okay. Now, omega then meaning square root k over m. So at this point, we want to pause, okay, and talk a little bit about what angular frequency is, frequency, and period. Okay. So your angular frequency has units of radians per second. It has a very similar interpretation to angular velocity from rotational motion. Okay. And this is why we need omega in our sine function, because radians per second times time radians per second times seconds is unitless. So remember the arguments of your trig functions and exponential functions need to be unitless. So this is the number of radians per second that your system moves through. Okay, now that's a bit of a fuzzy notion at this point. All right, so let's back up and define frequency, angular frequency, and period. So frequency, let's consider the oscillating mass. Okay, and let's say that the mass is oscillating, if this is the equilibrium position, and then it's oscillating between these two endpoints. Okay, and it's just going to oscillate between these. Your frequency is the number of cycles per time that your system goes through. Okay, so for example, let's say this spring mass system completed 3 cycles per second. Okay, then your frequency is equal to 3 hertz. Okay, so the units of hertz are cycles per second. Now, an entire cycle means it returns to its original position in the same point in its cycle. So what that means is, let's say we displaced the block out here, okay, and we released it, and then so the block came back, hit the equilibrium position, moved through it, came over to the x minimum position, and then came back. That would be one full cycle. Another example would be like pushing a child on a swing. If you start with the child pushing them from the back forward, then they swing forward, and then when they come back to the point where you pushed them from, that would be one complete cycle. Okay, so your frequency is just the number of complete cycles per unit time that you or that the system goes through. And in our case, we're going to measure that in cycles per second, which is hertz. Okay, now your angular frequency is radians per second. And the way that we think about this is, think of a unit circle, and if my starting position, like this would be x max, and then I let my system go. Halfway through the cycle later, it's at X minimum. So that would be like rotating through this circle halfway. And then when it comes back around, it completes the full cycle. So that would be 2 pi radians. So one complete cycle equals 2 pi radians in circular motion. Okay, so we're kind of drawing an analogy between the linear motion of the spring and the number of radians it's moving through if we were to translate it into circular motion. Okay, but this angular frequency omega, because we're moving around the circumference of this circle, returning back to your original position would be the number of cycles, but the circumference of this circle is 2 pi times that. So your angular frequency is equal to 2 pi times your normal frequency. Okay? And then your period is the time for one complete cycle. Okay? And we just labeled this T. But notice that time for one cycle and number of cycles per unit time are reciprocals of each other. So we say that our period T is equal to the reciprocal of our frequency. All right? But if our frequency is equal to 2 pi, or omega over 2 pi rather, then my period is also equal to 2 pi over omega. So we now reach one of the most fundamental relationships in oscillations. Okay? If I have a Hooke's law form of this, a mass on a spring, or something that can be modeled like a mass on a spring, then the angular frequency is the square root of the spring constant over the mass. And that means that I can directly predict what the period is by this relationship. Okay? So, my period is going to be 2 pi times m over k. Right? So if you know the mass and if you know the spring constant, you can immediately predict, as long as there's no friction and things like that, what the period of oscillation of your system ought to be. Okay? So let's do a quick example. Let's say we have a 1.5 kilogram object is attached to a spring of constant, not constant, let's make it nice. Say 150 newtons per meter. Okay? So we want to find the angular frequency, the frequency, and the period. All right? So again, assuming this is a frictionless system, and we're also going to assume that everything is horizontal, so we don't have any gravitational effects. I'll mention here in just a moment what to do with vertical springs. But we have this system. So omega is just the square root of k over m. And so in this case, this is going to be 150 newtons per meter divided by 1.5 kilograms. And so this is going to be the square root of 100. Now, let's actually do work through these units. Okay, so newtons are kilograms times meters per second squared per meter per kilogram. So my kilograms cancel, my meters cancel, and I'm left with 1 over second squared, and when I take the square root of that, it'll be 1 over seconds. And since radians are unitless, we can slap radians on there. So this is 10 radians per second. Okay. So if I translate this into the circle, right, 1 radian is about 57.3 degrees. So 1 radian is there. Obviously, all the way around is 2 pi radians. Which is about, 6.28. And then another pi puts you at, 9 point something. So like 10 radians would be 1 full revolution and a little bit more than another half. Okay. 10 rads, not 10 pi rads. Okay, so in 1 second, it went through a little bit more than 1.5 revolutions. All right. And then B, find the frequency. Since we know that F is equal to omega over 2 pi, we can say that this is going to be 10 divided by 2 pi. And if I do that, ten divided by 2 divided by pi, 1.59. So what this means is, if you were actually in the lab, okay, if you were actually in the lab with this system, you would measure that it took 1.59 that it went through 1.59 cycles every single second. Okay. Now, what you typically do in a system like this, if you're trying to actually measure the frequency, what you do is you typically will let it go for like 10 cycles, and you'll just let your stopwatch go, and then you'll stop your stopwatch at the end, and then you count the number of cycles and then divide it by the total time. Okay, so this is what you would actually measure for that frequency, right? And then the period is the reciprocal of this. So the reciprocal of 1.59 So it would take about 0.6 seconds for this particular system to go through one cycle. Okay, so that is, well, let's kind of sum things up for a moment. Okay, so the major points of this particular lecture are, if you have Hooke's law or a potential energy function like this, you will get oscillations when you displace your object from equilibrium, right? The angular frequency is going to be the square root of your spring constant divided by your mass. Your frequency, now we didn't explicitly write this one down, but we can get it from right here, combined with the fact that omega is the square root of k over m. Your frequency is 1 over 2 pi times k over m. And your period is equal to 2 pi square root m over k. Right? And let's actually do that last calculation and show that it agrees with finding the frequency and taking the reciprocal, right? This is useful. So square root m over k. So, whoop. No, I didn't want to do that either. Here we go. We want 2 pi. M is 1.5 kilograms. K was 150 newtons per meter. We're not going to go through the unit analysis again. Hopefully above was convincing. So if I take the reciprocal of radians per second, I will get time. And actually, as you can see, this is 0.01, and the square root of 0.01, so this whole calculation right here is 0.01. The square root of 0.01 is 0.1. 0.1 times 2 pi to 3 significant digits is 0.629. So you get the exact same answer. Okay, so it doesn't matter if you take the reciprocal of your frequency, if you have that, or if you take 2 pi times the square root of m over k as your period. Either way will get you the same answer. Okay, but these are the three fundamental relationships. So I really should say these are specific to springs, but general relationships are that the frequency is the reciprocal of your period, and your period is your reciprocal of your frequency. These are interchangeable, and that your period is equal to 2 pi over omega, and F is equal to 2 omega over 2 pi. Okay, so these are general relationships. Okay, so we will leave that for the moment. This is the first lecture on oscillations. Up next is pendulums.